Just in progress. Okay, I think yes, we are live. So welcome again. This is Tuesday, so it's time for a seminar, Tuesday seminar at Warsaw University Astronomical Observatory. And today we have a guest from our neighboring institute who unfortunately couldn't be here in person, Mirek Giersz, Professor Mirek Giersz, who's a professor at Nicolaus Copernicus Astronomical Center, Polish Academy of Sciences. And Mirek is going to tell us about black holes in clusters. Mirek, please.
Thank you, Łukasz. Good afternoon, everybody. I'm really very sorry that I couldn't come to the observatory in person. Thank you very much for inviting me and allowing me to present the results of work of my group and my work. This is my first talk in the Astronomical Observatory after a long time. My last presentation was in 2015, so I decided to give you a more general introduction to globular cluster evolution and to the method used to study it. I'm going to talk about the evolution of globular cluster and their black hole populations. The main collaborators of the work are listed here. And there is a very long list, but without their substantial input, it would not be possible to carry out and complete many important projects. As I already said, I'm going to give you a short introduction to the physics of the evolution of star cluster and to discuss the Monte Carlo method and the MOCCA code. I will try my best and hope to finish in time. If I am running out of time, I will skip some slides or their part. The outline of the talk is following. In the first, very briefly, I will discuss the fundamental physical processes behind the different phases of star cluster evolution, and then I will introduce the MOCCA code. In the next part of the talk, I will discuss the physical processes which shape the population of black holes in star cluster environment. So let's start with the general picture of star cluster evolution. A star cluster evolves thanks to the relaxation process, the uncorrelated, very distant gravitational interaction of stars with all other stars in the system. Relaxation alters the energy and angular momentum of each star. The time scale of the whole system evolution is proportional to the half-mass relaxation time. Here is the formula, which, as you can see, depends on the number of stars in the cluster, or the mass of the cluster, and the half-mass radius, or the characteristic radius of the cluster. So larger and more massive cluster evolve slower. They have a larger half-mass relaxation time. One of the consequences of the relaxation process is mass segregation. Massive stars are losing energy and sink to the center of the cluster. Another consequence is approaching the energy equipartition. Stars with different masses have similar kinetic energy. Cluster evolution proceeds through a sequence of slowly changing equilibrium states described by the virium equilibrium, in which the absolute value of the total potential energy is twice as the total kinetic energy. Let's ask a question. How will a cluster evolve if it loses mass or kinetic energy because of star escape? Using the virial equilibrium, we can derive some equation which connects the old and the new characteristic parameters of the cluster after removal of mass or kinetic energy. So as you can see from this equation, when we are removing the mass, the characteristic radius is increasing and the velocity, the characteristic velocity is decreasing. When we are removing the kinetic energy, the characteristic radius is decreasing and the characteristic velocity is increasing. So if we have the energy generation, so we have some kind of energy source in the center of the cluster, this energy source leads to cluster cooling and expansion. So this is this behavior is a consequence of the negative heat capacity for self-gravitating system and is very similar, generally the same in the stars. And this leads to two important phases of cluster evolution. The structure of a star cluster can be described as a dense core and extended halo. If in the stellar system there is a sufficient density gradient between the core and the halo, then the central parts are described in an approximation by an isothermal distribution. The halo serves as a heat reservoir. The core loses energy and as transferred it to the halo, and it collapses and heats up, as we seen in the previous slide. So the core, so the process speeds up, and it's called a gravothermal collapse. The core collapse is self-similar and takes about 330 central relaxation time. The core collapse can be stopped by energy generated in dynamical interaction by just form free-body binaries. We know that interaction between binaries and other stars can extract binding energy from binaries and hit the system. This means increased kinetic energy. And we know from the previous slide that this will change the behavior of the system. Instead of collapsing, the core will expand. So if the energy generation is very sufficient in the core, the velocity in the core can become smaller than in the surrounding region of, so the heat, instead of flowing from the center to the outside of the core, will flow from the outside into the core, and this will lead to faster and faster expansion of the central part of the cluster. This is the gravothermal expansion followed by the gravothermal collapse. So in the system is expand and then will again collapse. The phenomenon is called the gravothermal oscillations. So the theory I just described was initially developed for single mass isolated cluster approximated by self-gravitating gas. As you can see from these plots, it works perfectly. So in this plot, you can see the core collapse and the post-collapse evolution of the Fokker-Planck model of the small n-body, small star cluster. We see the collapse and then expansion. But in this figure, you can see here is the central density and here is the time in particular units. Then you can see this gravothermal oscillations, which are quasi-periodic oscillation with the very large amplitude of several orders of magnitude. So we can, nevertheless, this perfect agreement with the theory. Nevertheless, there were a lot of controversies connected with the stellar mass spectrum, stellar evolution, stochasticity of energy generation, and influence of the galaxy tidal field. The gravothermal oscillation were confirmed in many simulations, as you can, seen, in many simulations of star cluster done with different types of numerical codes, from gaseous through Fokker-Planck, Monte Carlo to n-body codes. We can ask the question: does the just described picture work also for real large star cluster where all processes mentioned just before work together, shaping the cluster evolution? So as you can see from this figure, we can see in the Monte Carlo simulation of star cluster without primordial binaries and without stellar evolution, but with with the mass spectrum, we can see and tidally limited cluster, we can see very clear gravothermal oscillations. But when we look at the cluster in which we have the stellar evolution, primordial binaries, formation of the black holes, and so on, then we see that gravothermal oscillations are only visible at the end of the cluster and the cluster evolution. And most of the cluster evolution is governed by the primordial binaries, and the formation of the black hole subsystem. And I will concentrate mostly on this part of the cluster evolution in my talk. Generally, star cluster evolution is very similar to the well-known evolution of stars. The pre-main sequence evolution of stars is very similar to the core collapse of our cluster. The energy needed to sustain the cluster or star structure comes from the potential energy of collapsing central part of the star or the cluster. The main sequence phase for stars is similar to the post-collapse phase for cluster. The energy source for stars is connected with thermonuclear reactions, and for cluster is connected with binary binding energy extracted during the dynamical interaction. The star depth is connected with potential energy, thermonuclear energy generated in the shells and enhanced stellar winds. For cluster, the depth is connected with enhanced cluster stripping by tidal forces and enhanced rate of binary energy generation. The main difference between stars and cluster is that the massive stars evolve faster and massive clusters slower. The thermonuclear energy source is more effective for massive stars with larger densities and temperature. For cluster, the relaxation process, which controls cluster evolution, is slower for massive clusters. Interestingly, the final stages of the evolution of stars or clusters are very similar, involving very rapid phases of mass removal and formation of a compact object or total disintegration. For example, supernova for stars, or so-called dark cluster for star clusters. So dark cluster is the cluster which contains in the center IMBH with small addition of ordinary stars, or the black hole subsystem with addition of small addition of ordinary stars. Star cluster seems to be objects whose evolution can be relatively easy simulated numerically. They are almost spherically symmetrical and in virial equilibrium. They are only slightly influenced by the environment in which they live. Unfortunately, this is not true. If we want to simulate real cluster from birth to death, we need to account for a variety of physical processes characterized by very divergent timescales and dominant in different epochs of cluster evolution. They are residual gas removal at the formation of the star cluster, stellar binary evolution, mainly important at the beginning of cluster evolution, relaxation, which governs the whole cluster speed of evolution, variety of dynamical interaction between stars and binaries, dissipative interaction connected with tidal interaction, gravitational wave radiation, galactic tides, and many, many, many more. Every physical process is connected with its own characteristic timescale. So we need to cover timescales from milliseconds for collision time for black holes or neutron star to gigayears for star cluster evolution time, and spatial scales from kilometers for neutron star or black holes of stellar mass to parsecs for cluster size. This is at least 14 to 17 orders of magnitude. This is extremely challenging for any numerical code. Additionally, if we want to track any population of objects living in star cluster, we need to efficiently handle terabytes of data to analyze them in a manner similar to observational data processing. This also comes with many, many challenges, not smaller than the challenges which we have to simulate evolution of real star cluster. So there are at present two numerical methods used to simulate star cluster evolution, namely N-body and Monte Carlo codes. The N-body method can be regarded as a brutal force method in which all mutual gravitational interaction between all bodies in the cluster are computed. As you can see in this slide, there are a lot of advantages of this method, but there is one disadvantage, very serious one. The speed of the code, even when we apply different tricks which helps to efficiently compute the gravitational force between all interacting objects, and we use the newest hardware with the GPU accelerators. The simulation time is proportional to n squared log n. So this is relatively slow. So we are unable to run really very, very big n-body simulation of real evolution of real star cluster. The Monte Carlo method was developed to overcome those problems. It uses physical knowledge about the relaxation process and efficiently utilize a cluster spherical structure. It is fast. The simulation time is proportional to n log n. So in time needed for the n-body code to simulate one real globular cluster, this is right now about half a year. Hundreds of thousands of star clusters can be simulated with a Monte Carlo method. The Monte Carlo method is ideal for conducting surveys of star cluster models and then analyzing them statistically. So this is a big advantage of the Monte Carlo method. Okay. The foundation of the Monte Carlo method is as follows. A star cluster is treated as a collection of spherical shells, each one representing a single object. A shell is characterized by mass, energy, and angular momentum. Knowing potential distribution, because there is a spherical symmetry, there is an easy way of picking up a new object position. There is no need for numerical orbit integration, so the computation time is proportional to n. The relaxation process of an object with all other objects is approximated by just one interaction of two neighboring shells. This is the so-called Hennon's trick. So the computational time for the relaxation process is proportional again to n. A cluster is divided into so-called superzones. Each superzone is evolving on its own relaxation time. So the Brock time step scheme assures that the evolution of the cluster in any spatial scale is properly reproduced and is conducted with its own relaxation timescale. There are currently 3 independent Monte Carlo codes, all based on the Hennon method, which was developed in the 70s of the last century, and then substantially upgraded by Stodulkiewicz in the 80s of the last century. And these 3 groups are connected with Northwestern University. This is Fred Rashio's group, with Bologna University, Antonio Solima, and my group. So the MOCCA, Monte Carlo, was developed by my group for over 25 years. So this is a long history of developing the code. So the present version of the MOCCA code, in the present version of the MOCCA code, the following physical processes are implemented. Here is the very long list. And all these processes covers all the most important physical processes which can influence globular cluster evolution and or evolution of any objects or their population living in the cluster. The MOCCA code at present is one of the most developed numerical codes to follow the evolution of real star cluster. It was very successfully tested against the various n-body simulation. The Monte Carlo code developed at Fred Rashio group is on the similar level. So after this a little too long introduction to the evolution of star clusters and numerical methods used to simulate their evolution, it's time to concentrate on black holes, the influence on star cluster evolution and the observational signature which they can provide. Let's start with black hole subsystem. For the standard initial mass function, about 1,000 of all stars in the star cluster will form black holes. Some of them will be ejected because supernova natal kicks. Black holes are the most massive stars in the system, so they will segregate to the cluster center and finally form black hole subsystem, which is a dense mixture of black holes and ordinary stars. Black holes will strongly dynamically interact between themselves, form binaries, and generate energy in the interaction with the surrounding objects. It was assumed for many years that such an interaction would lead to the rapid removal of black holes from the system, so they should not play a significant role in cluster evolution. Recently, Brin and Heggie showed that this is not the case. The evolution of black hole subsystem is controlled by energy flow through the half-mass radius, so it is controlled by the global cluster evolution timescale, not by much shorter black hole subsystem relaxation time. So black hole subsystem can survive for times comparable with the cluster age. The efficiency of energy generation in black hole subsystem has to adjust to the energy flow to the half-mass radius. The larger energy efficiency, the larger core radius, the smaller density for the same mass of the cluster and the same half-mass radius. So this simple consideration leads to four phases of cluster evolution, which are sketched here on this picture. The first phase is connected with very fast mass segregation, formation of the black hole subsystem, and the core collapse. So when the density is large enough, binaries start to interact with other stars and start to generate energy. So the core collapse is stopped, we have the core bounced, and we enter the next stage of the evolution, so-called balance evolution, in which the energy generated in the black hole subsystem is exactly the energy which flows through the half-mass radius of the star cluster. So this is the second phase. So we know that to generate energy by binaries, we need interaction with other stars, and interactions at some point will lead to kick out of the binaries from the system, and the formation of the binaries usually is more probable for the most massive objects. So first, the most massive black holes will form binaries, and then they will interact with other black holes and stars, and then finally kick out from the system. So then the next a little bit lower mass black holes binaries will be formed, and so on and so on. But lower mass black hole binaries means smaller energy efficiency, generation of energy efficiency. So this means that we need a little bit to collapse core to get the higher density, to have the larger rate of interaction, to compensate the smaller energy which is generated by binary. So this is the third phase. In this third phase, the black hole subsystem is slowly depleted, and then when it is depleted, finally the core is collapsing further, and the binaries from ordinary stars are formed. We have the second core collapse, and then post-collapse evolution, which is really very well known from the standard simulation of star clusters without black holes and with single mass system. So let's see if this picture works for real star cluster. Consider two models of star cluster. In one model, all black holes are kicked out from the system because of supernova explosion. In another model, because of mass fallback, black holes receive smaller natal kicks during supernova explosion. In such a case, substantial number of black holes will stay in the cluster and form black hole subsystem. Both models are initially tidally filling, which means that the stars are distributed up to the cluster tidal radius. This is important. This means that much likely, like as a star filling its rho slope in binary system. So this condition is really very important. for the further discussion of the evolution of the black hole subsystem. So, as you can see from this figure, when we have the black hole subsystem form in the cluster, the evolution of the cluster is much faster than in the case of the evolution when we don't have black holes in the cluster. So, at the end of the evolution, system loses its balance and enters the dynamical disruption, the phase of the dynamical disruption. So generally, this faster disruption of star cluster doesn't depend on the number of black holes, number of primordial binaries, tidal radius, but the cluster has to be tidally filling. This is important. So we can see that at the end of at the time when the cluster is dissolved, still in the system there is a substantial number of black holes, and usually the system starts to enter the fast dissolution phase at the time when the mass of the cluster is about 20% of the initial mass, and the mass of the black hole subsystem is about 2% of the cluster mass. So we can look in this figure on the evolution of the virial ratio for different groups of the objects in star cluster. In the black dots, we can have black holes. In the blue, we have other objects in the system, but in green and red, we have the whole system. So as you can see, the black holes very quickly decouple from the other stars and become very, very cold. But other stars become a little bit hotter. So we see that the formation of the black hole subsystem is connected with the decoupling, practically decoupling of the black hole subsystem from the rest of the cluster, in the sense of its virial ratio, because we know that this is not real decoupling, because there's a connection between the black hole subsystem and other stars in the cluster, because the interaction through the interaction between black hole binaries and the other objects in the core, and then they are kicked out from the central part of the system and transfer energy to the other parts of the cluster. So to understand the physical mechanics behind the dynamical dissolution, we should look at the evolution of the escape velocity in this figure. The red line is for the black hole subsystem, and the black line is the system without black hole subsystem, and without black holes in the cluster. In the late phase of evolution, the cluster is constantly tidally stripped. We remember that we have the tidally filling cluster, but the inner structure of the cluster doesn't change very much. So as a result, the escape velocity becomes smaller and smaller, because it will only depend on the total cluster mass, not on the structure of the cluster. A lower central escape velocity also means a lower central velocity dispersion and correspondingly higher rate of dynamical interaction, as well as greater escape rate. Such positive feedback leads to the rapid disintegration of the cluster on a dynamical timescale. We see this here. So just before the final dissolution, cluster should look like a dark cluster, for the first time theoretically predicted by Banerjee and Krupa in 2011, as it was shown by Askar et al. At 2017, NGC 6535 could be such a cluster. So this is the Milky Way globular cluster. And this conclusion was derived on the basis of the MOCCA simulation of real star clusters. So we already learned that the black holes should be present in star cluster for most of their evolution. So they should dynamically interact between themselves and also with other stars. Such interactions will lead to disruption or changing of binary properties, and then the preventing of black hole mergers that would otherwise have merged due to isolated binary evolution. Of course, different group of binaries whose properties will not lead to black hole mergers due to isolated binary evolution will change their properties in dynamical interaction and be forced to merge because of isolated binary evolution. Then there should also be another group of binaries that will directly lead to black hole merger during many types of dynamical interactions. The efficiency of each channel depends on the cluster density and its mass. Generally, there are three environments for black hole mergers. Field, this is in the field outside star cluster. In low N cluster, this is open cluster or young massive clusters, or large N and dense cluster like globular cluster and nuclear star clusters. So each channel should be characterized by different masses and mass ratios and spins of black hole mergers. The LIGO-Virgo-Kagra collaboration has already observed about 100 black holes black hole and neutron star mergers, and this should allow to draw some conclusions about black holes and neutron star properties. But because of low statistics and many uncertainties in physical description of different merger channels, this is still problematic. In this slide, you can see typical sequence of events leading to black hole or neutron star mergers in dense cluster environment. As you can see, black hole or neutron star are involved with dozens of dynamical interactions. So there are the binary formation, flybys, exchanges, mergers, and some events connected with binary stellar evolution, common envelope phases. And there are dozens of such a interaction, which finally will lead to the formation at the end black hole binary or neutron star binary. So the processes leading to compact object mergers in star cluster are extremely stochastic and depend on the cluster density and then the efficiency of keeping black holes and neutron star in star cluster. So if we can imagine if during some of this interaction binary will be kicked out or the single black hole or neutron star will be kicked out from the system, this whole sequence of interaction will not lead to the formation of the black hole binary or neutron star binary. Generally, there are 4 physical processes leading to the ejection of black holes and neutron star from star cluster. There are relaxation process, kicks during dynamical interactions, supernova formation kicks, and gravitational wave radiation kicks. Relaxation process, together with the galactic tidal field, is responsible for removal so-called potential escapers, objects whose binding energy is just above the tidal energy. Kicks during dynamical interaction are connected with binaries and their interaction with other objects in the system. Binaries whose binding energy is greater than the average kinetic energy in the system are called hard binaries, and they become, on average, harder during dynamical interaction. Each dynamical interaction with a hard binary, because of momentum conservation, is connected with velocity kicks. So if the binary is hard enough, it will be kicked out of the system or before merge. We have to remember that before kicking out binary, we will kick much more larger number of intruders which interact with this binary. So the intruders can be also the neutron stars or black holes. We know that during supernova explosion, a substantial part of the stellar mass is expelled with very large velocities, again, because of momentum conservation. Neutron stars and black holes receive large velocity kicks. Black holes with velocity kicks, black hole velocity kicks can be reduced for massive stars because of mass fallback. As you can see from this figure, when we see the mass fallback parameter and mass of the black hole, for the massive black holes, mass fallback is practically 1. This means that black holes will not receive any velocity kick during supernova explosion, so they will stay in the system. And of course, if the system is very dense and massive, the escape velocity is large, so the lower mass black holes as well will stay in the system. They will be not kicked out from the system because of the supernova explosion. The figures is this figure is a little bit scattered, so it is not as it should be. We should expect from the evolution of binaries in the field, because some of these points which are outside of these lines comes from the previous interaction in the dense stellar environment. So there are mergers of the binaries before the black hole formations. So we know that that merged black holes can receive gravitational wave radiation kicks. The amplitude of these kicks depend on the black hole mass ratio and black hole spins and their alignment with orbital angular momentum. Usually such a kicks can produce very large velocities up to 1,000 kilometers per second, unless the mass ratio is very small. So we can expect that merged black holes will be very efficiently kicked out from the cluster. So, as you can see from these plots, which plots based on more than 2,000 MOCCA simulation of real star cluster, the retention fraction of black holes is changing with the cluster evolution time and with the cluster type. So if we have the cluster type of evolution, so if we have black hole subsystem in the cluster, the retention fraction is relatively small, about 10%. But when we form massive IMBH, the retention fraction is really very large. It's about 80 or even more percent. And this is because the mass of the IMBH is much, much larger than the mass of the stellar mass black hole. So the mass ratio is very small, and then the gravitational wave radiation kicks are much smaller than the escape velocity. So generally, the larger the cluster concentration, the larger the retention fraction of the black hole merger product. Recently was observed the first merger in which an IMBH was formed, and black holes involved in the merger event had masses in the second black hole mass gap connected with the per instability supernova. This event is called GW190521. The theoretical explanation for such a high mass merger is challenging on the ground of only isolated stellar and binary evolution. It can be more easily explained on the ground of stellar dynamics. One of the scenarios is connected with the chain of black hole mergers in dense star cluster. And as you can see from this plot, which is it shows the result of the n-body simulation of young massive and dense star cluster done by Arcaseta and others, that we can create a similar black hole to the observed GW190521, not only the mass, but as well the spin, when we have the 3 successive mergers between black holes. So this is the chain of mergers. But we know that the gravitational wave radiation kicks could be very large, and then it would be very difficult to keep such a merger products in each generation in the cluster. So the probability to form such an object in the sequence of merger is really extremely low in the globular cluster and open and even dense star cluster. But it is possible in the nuclear star cluster when the escape velocity can be really very, very large, and then the probability of keeping the final product in the system is not negligible. Another possibility, the possibility is to connected with runaway mergers between main sequence stars that lead to the formation of stars with masses of several hundred solar masses or even larger. Such a massive star can directly collapse to black hole or collide with solar mass black hole and form massive IMPH. The mass of IMPH will depend on the amount of mass accreted onto a black hole. The amount of accreted mass is very uncertain and depends on many factors, but is definitely larger than zero. It can be as large as about 20%, as suggested by observation and theoreticians. I will return to this scenario shortly. Recently, Costa et al. And Veron et al. Proposed another scenario in which a massive helium core-bearing star collide with a massive main sequence star and then collapse to black hole, avoiding a pair instability supernova because of the small mass of the helium core. So in this scenario, we can form black holes in the second mass gap. So, but please keep in mind that all these scenarios which are discussed here need really dense stellar environment in which we can have frequent mergers between stars and frequent interactions between stars. Otherwise, we will not produce needed masses of the black holes. So this means in the second mass gap. So we know that in star cluster an IMPH could be formed because of dynamical interaction. There are usually listed 4 scenarios in which IMPH can be formed in the different environments, not only in star clusters. And right now I would like to discuss the scenario which leads to the formation of the IMPHs in dense star cluster, and this scenario based on more than 2000 MOCCA simulation of real star cluster. As you can see, we from this figure, we can have 2 different scenarios. The first scenario in which we have a runaway merger of main sequence stars and then collision with the black holes or the direct collapse to form IMPH. And in this scenario, the formation of IMPH is very fast. The first few hundred million years, it is formed IMPH with masses over 1000 solar mass. And there is a slow scenario in which we have to wait until the black hole subsystem is kicked out from the cluster, and then ordinary collapse will proceed, and the ordinary post-collapse evolution. And in this scenario, only a handful of black holes stay in the system, and they form binaries. They interact with other stars, and because of the mass transfer, collisions, mergers, they build up mass in a slow process, and eventually they can enter the mass of the IMPH around 1000 solar masses. So the efficiency of IMPH formation depends on the amount of the mass accreted onto the black hole. This is in the first scenario. This is very important. If the mass is practically 0, we will not form IMPH in the first scenario. We have to wait until the direct collapse of this very massive object, but this is as well not a very well understood process, because runaway mergers will produce very massive main sequence stars, but they will be out of the equilibrium. So nobody knows how much they will lose the mass because of the winds, or if they are unstable, maybe they will disrupt themselves. Okay, so we can ask if it is possible to kick out IMBHs from the cluster due to dynamical interaction. We know that IMBHs are really very massive objects. So to kick them out from the system, we will need binaries with masses which are comparable to the mass of the IMBH, and very hard binaries, because we need a huge amount of the energy generated during the interaction to increase the velocity after the interaction to the level which is larger than the escape velocity. So it was believed that it is very difficult to kick out IMBHs from the star cluster, but looking at the simulation which we did, the MOCCA simulation of the real star cluster evolution, in which we form a lot of IMBHs, we saw as well a lot of IMBHs which are kicked out from the system. So in this figure, you can see the escaping mass of IMBH in solar masses and the mass ratio between IMBH and the intruder. So you can see that the mass ratio is not really very large. It's a bunch of the masses of the intruder, which are much smaller than the mass of the IMBH, which is kicked out. And in this figure, you can see the time of escape. It is usually at the very beginning of star cluster evolution, when the black hole subsystem is still present in the cluster, and the escape velocity. We see there is a bunch of the escapers with relatively very small velocities. So this means that usually the black hole binary with IMBH is interacting with other massive objects in the system, black holes, and it slowly gains the velocity, and it moves on the more and more elongated orbits, and then at the end it becomes a potential escaper, and it escapes from the cluster with relatively very small velocity. So such IMBHs can stay close to the globular cluster, and probably they will stay close as well to the globular cluster tidal tails. So this is a quite interesting observational hint. Maybe we should look for IMBHs in the tidal tails of globular clusters. So at the end of my talk, I would like to present very interesting results of Agostino Levec's PhD thesis. Agostino is my student who worked on populating external galaxies with globular clusters from MOCCA models. I hope that he will defend his thesis before the summer holiday. I'm not going to describe every detail of his models. If you are interested, please refer to his papers. I will show you just some of the results of his work, results that show the potential of the machinery he developed. In the presented figures, you can see the kinematical properties of globular clusters in the Milky Way. And this is orbital eccentricity, mass, and the distance. And as you can see, the agreement between the observational properties, red line, and the model properties are very, very, very good. The same is as well for the structure parameters of globular cluster, like half-light radius. We have a very good agreement between the observation of and the model. The same is for the Andromeda galaxy. We again get very, very good agreement between the observation and the Agostino's model. So using his model, we can try to infer the number of distribution in a galactocentric distance of exotic objects living in globular cluster. I will concentrate on black hole binaries. So as you can see from this figure, when here we have the distance, and here is the total number of black hole binaries in the distance shell. So we can see very clear dependence on the galactocentric distance. The larger number of black hole binaries we should observe in the closer to the galactic center. But when we look on the average globular cluster, we see here that there is practically 1 or 2 black hole binaries per cluster. So, and it seems that there is no very strong dependence on the galactocentric distance. The shadowed region is just plus minus 1 sigma from the average value. So, in contrary, it seems that the properties of black hole subsystem depend on the galactocentric distance. The average eccentricity and the average mass ratio seems to strongly depend on the galactocentric distance. The larger values are closer to the galactic center, and smaller are outside and farther outside. But what is interesting, the average value of the same major axis of black hole binary doesn't seem to depend on the galactocentric distance. It is of the order of 0.5 × 10⁴ solar radii. So this means several thousands of astronomical units. So there are very wide binaries, black hole binaries. So this very strange dependence on the galactocentric distance is difficult to theoretically understand, and more simulations and work is needed to explain this relatively strange behavior. So what is important, the same analysis can be done for other exotic objects like tidal disruption events, world axis, low mass X-ray binaries, cataclysmic variables, and many more. And what is interesting, student Corner Hovil, during his summer student internship, analyzed using the results of Agostino Levesque's work, the millisecond microlasing events and their distribution in the galactic field. The work still is ongoing, but the first results are very promising, showing large number of microlensing events on massive black holes. So hopefully this work will be finished, and we will provide quite interesting results about the microlensing events in globular cluster and their distribution in the galactic field. I hope that I convinced you that evolution of black hole population in star cluster can lead to the formation of many interesting merger and collision products which otherwise would not be produced. Such objects will have very distinct observational properties. Still more detailed theoretical, numerical, and observational studies are needed to better understand the observational signatures, the influence of the environment on their evolution, and their feedback on cluster evolution. So we are working right now to develop further the Monte Carlo code in the direction connected with better description of dissipative processes connected with the tidal interaction, gravitational wave radiation, better description of the mass accreted onto black holes during mergers and collision with different type of stars. This can be very important effect when we have the mass transfer of the black hole during the interaction with the ordinary binary, for example. And then we will try to follow black hole spin evolution during dynamical interaction. This is very important for the gravitational wave radiation kick. We can easily imagine that there are a huge amount of the flybys in a star cluster when we can assume that at the formation, the spins of the black holes are aligned with the angular momentum of the binary. But during the flybys, only flybys, not the exchanges or very strong interactions. But during the flybys, we can imagine that the black hole spins will not change direction, but the angular momentum direction will change, and this will influence as well the gravitational wave radiation kicks. And then we will look on the multiple star population and the influence on the black hole subsystem on the cluster dissolution. Thank you very much for your attention.
Thank you. Thank you very much, Mirek. Are there questions here first?
Hello, Mirek. So you mentioned these exotic objects like binary black holes with the orbital separations that are quite large. So are there any chances of observing them and verifying these predictions?
I don't think so that it will be easy to observe such a black hole binaries. They will definitely not merge in the Hubble time because of the gravitational wave radiation. Only chance to observe them is during some kind of interactions when we have close passages of the ordinary stars, and maybe we can see some X-ray radiation, and from this and variation of this X-ray radiation we can infer that there is a black hole binary.
Okay, more questions here? I have one quick question. So I'm very much intrigued by these free-floating IMBHs you predict to exist. So how many of them you expect in the Milky Way?
So this is a good question. So to find out how many of these IMBHs we can expect in the Milky Way, we will need to use Agostino's machinery to infer the distribution of this escape IMBHs in the galactic field. This is not yet done, but it is. We are probably will look at this when we have much more good models of globular cluster, because right now we are preparing to run thousands of Monte Carlo of MOCCA models of real star cluster models with the multiple stellar population. So models which will guarantee that the observed ratio between the first and the second population of the stars in globular cluster is properly reproduced. And these models needs very different initial conditions than the models which were run for the survey which I showed you, because to keep the observed ratio for between the first and the second population in the cluster, we need to start with the very clusters which are close to the galactic center, very massive ones, and only tidally filling clusters. So the previous models were tidally underfilling. So with the tidally filling models, we will not form as many IMBHs, and for the tidally filling model, when the underfilling model where the density is much larger. So it is difficult to say right now. So we have to analyze the new first to run the simulation and then analyze with the Agostino's machinery. But I think that it should be definitely not negligible value, because the number which you showed, which I showed in this plots, comes from only about 100 models. So, and we have similar number of kicked out IMBHs from the cluster. So I hope that this will be not negligible.
Okay, thank you. The last question is from Dorota from Zoom. Dorota?
Hi, I have two questions. The first one is, how massive in your calculation first generation black hole could be? I mean, if you, how you are taking into account this per instability gap. So how massive this black holes could be? The first generation before just making dynamical interaction and so on.
Okay, so this is about 40 something solar mass. It depends on the metallicity.
So you don't have, let's say, something what is corresponding to the gap that you can produce more massive than that, let's say, 100 solar masses?
Because of the per instability gap, I cannot produce the black holes with the standard binary evolution more massive than about 40 something solar masses.
Okay. And the second question is it is connected with different kind of clusters. I mean, what are the main difference if you compare open cluster simulation and globular cluster simulation, if you take into account the properties of black holes? Can we say that we have more massive if there are globular clusters, or maybe the other things? Can we say something if the origin of this particular system is from open cluster or globular cluster?
Yes, of course. So the properties of the black hole binaries will strongly depend on the type of the cluster in which they exist. So generally, this is connected with the kick velocity and the escape velocity. So if you have a low mass cluster, the escape velocity is very small. So you don't need to have very compact black hole binaries to be kicked out, for example, from the cluster. So if the mass of the cluster is much larger, the escape velocity is much larger. So to kick out the binary from the cluster, it has to be very tight one. And then because of the, for example, excitation of the eccentricity, before this, it can merge before of kicking out it from the cluster. So this is
the main difference.
This is the main difference. Escape velocity. This is main difference. So generally, if you look at the kicked out black holes from the black hole binaries from the cluster, in the open cluster, you have definitely more wider black holes binaries than in the more massive cluster. But of course, everything depends on this very early stage of the cluster evolution, when you have the core collapse, the first core collapse connected with the mass segregation. And then most of the interaction are happening at this time, and the density is really very, very large, and the escape velocity is a little bit larger. So you can expect that some of the binaries will be more compact than in the when we are looking on the average properties of the cluster.
Okay, thanks a lot. Thank you.
Okay, thank you very much, Mirek, for your seminar. Thank you all for attending. So let's
thank you very much.
Thank you and goodbye.
Bye-bye.